students, pleasure to welcome you again, and I hope that Dr. Perot's videos were helpful in explaining the procedures that we're going to carry out. And in this section here, we're going to go over the calibration of the calorimeter. We're going to study why we have to calibrate the calorimeter and how we go about it. And we'll use a sample set of data to do some sample calculations, all right? So let's start out by going to our dock camera here so we can work a little bit on the theory. All right, let's go there. Okay, here we are. I'm going to use my phone camera here to serve as a makeshift dock camera. And let's talk about the theory behind this experiment, okay? Here with this little paper here, we're going to call this the calibration of the calorimeter. So our experiment, if you look back on your procedures here, and remember that you are given your procedures straight from a lab manual where everything seems kind of very dense here. And what you've been asked is to convert this into an outline form, like a step-by-step type of outline, right? So as you read through, you'll realize that what you're actually going to be doing here is you're going to be mixing some cold water. I'm going to call it just cold water at a temperature that you're going to measure. I'm going to call it T1. And you're going to mix it with some tap water, which I'm going to call, for the sake of illustration, I'm going to call it warm water. It's not warmed, it's just that it's from the tap. And that one, we're going to take also its temperature. We're going to call that T sub 2. Now, this is basically when you mix, then you have the same substance. And also, you are mixing equal amounts of the water at each temperature. So that means that whatever temperature change you observe here should be due simply to the difference between the temperatures of the cold and the tap or warm water. And we're going to call that T final. Now, ideally, what should happen is, just like in an example I give in lecture with 2 tanks of water kind of getting filled, right? Ideally, the final temperature should be essentially the midpoint between the 2 temperatures here. Right? So it should be T1 plus T2 divided by 2, the half point between the 2 temperatures. But in reality, what we observe is that typically what will happen is that this T final is a little larger, a little higher than the midpoint between the cold and the warm water temperatures. And the question we have to ask ourselves is, why is that? Okay, well, let me put a sketch here. I apologize for my poor sketching abilities, but let's pretend that I take my calorimeter. Remember, it's a double styrofoam cup. And let's say that I kind of zoom in and I look at the, let's call it the wall of the calorimeter. In other words, we're going to kind of like take a slice through and pretend that we actually see the wall of the calorimeter. I'm going to draw a little block here, and this is the calorimeter. Again, so for my poor sketching abilities. And then over here is the outside, which is basically, air at room temperature. And here is the inside of the calorimeter, where you have essentially the water. Let me pretend that I'm doing some. Sorry about that. Okay, now, the idea here is that we said that at the end of the process, you should have arrived at a temperature that was kind of like the midpoint between the 2 temperatures. But here's the thing. The calorimeter, although it is meant to be an insulator, it's not a perfect insulator. And remember, the outside of the calorimeter is at a temperature, right? which is essentially the room temperature. And if you do a simple calculation or just reason a little bit about it, you'll realize that that temperature is higher than the projected average or midpoint of the cold and the warm water temperatures. So what does that mean? It means there's a temperature gradient between the outside and the inside of the calorimeter. And although the calorimeter is an insulator, it still will allow a little bit of heat to be exchanged here. Of course, it has to go from the higher to the lower temperature. That is the heat that causes the final temperature to be higher than what we projected it to be based on the midpoint between the cold and the warm water initial temperatures. And our task now is to find out, well, how much heat capacity does this calorimeter have? And essentially, how much heat does it allow to be converted? Okay, so let's look at the math again. I'm going to do a little division here. So that's the theory. Now let's look at what is happening thermodynamics wise. All right. So we said that in any kind of process, the total heat that we will observe transacted here should be whatever exchange of heat happened to the water plus whatever exchange of heat happened to the calorimeter. But according to the law of conservation of energy, we should have essentially a isolated system inside the calorimeter. So there should be no net change in energy. Whatever transaction the water undergoes equals, the change in the calorimeter, and so they add up to zero. So this is, like I said, due to the conservation of energy, all that we studied earlier in the lectures. And what we're going to say is, let's rearrange this expression to say that essentially the heat exchange for the calorimeter would be negative of the heat exchange for the water. Sorry, my cue is kind of a little weird. Sorry about that. Okay, now let's see what these are. Now, one thing that's important is to remember that when we talk here about the heat exchange in the water, okay, this is not the heat exchange between the cold and the warm water. Okay, that's not what we're talking about. We're not talking about this exchange that we started studying on, which was the exchange between the cold and the warm water. That's not what we're talking about. No, we are talking about the transaction that caused the final temperature to be higher than the predicted midpoint between the cold and the warm temperatures. Okay, we're talking about this heat exchange. So this is the heat exchange we're talking about for the water. Okay, so what we're going to do now is let's see what each one of these is. Well, as we studied in class, the heat for a calorimeter is based on what is the heat capacity of the calorimeter times the change in temperature. Well, the change in temperature, excuse me, for the calorimeter started at room temperature, and then when we mixed in the waters, it ended up at T final. So final minus initial, T final minus room temperature. Now you can already see something here. What you can think of is, well, since the room temperature is bigger, that means that this is going to be a negative number overall. Okay, let's look at the other side of the equation. And of course, this would be in degrees Celsius over here. Now, what would be the heat exchange for the water? Remember, it's negative, so I'm going to put a negative there. It'll be the mass of the water, which we're going to calculate. We're not going to weight the water. We're going to basically put in a value based on the density, right? This would be times the specific heat of the water, right? Times the change in temperature of the water. So we call it famous cat. Right? Now, one thing that's important is the following. Remember, this temperature change in the water, we're talking not about between the cold and the warm water, but between what the temperature should have been versus what it ends up being per se. So this delta T of water here is actually the difference between the actual temperature the water landed at minus the temperature that the water should have landed at if there had been no exchange of heat through the calorimeter. Right? So very important you remember that. Now, let's look at these different things. First of all, the final temperature is something that we are going to determine. I'm going to show you that how we're going to determine that. The other temperatures, for example, the room temperature, we're going to measure that. We know what's going to be the initial temperature. We know what the cold temperature and the warm, quote unquote, temperature. So we can, basically calculate this number here. Again, we have the final temperature. We are going to determine the mass of water. We'll have that. And then the specific heat of water is a constant that we can look up. So essentially, our unknown is the heat capacity of the calorimeter. This is our unknown. And what we're going to do is we are going to solve, so we can calculate and solve this equation in order to calculate what is the heat capacity of our calorimeter. Okay, so this is kind of the theory. It explains why the final temperature is not what it should be, but the experiment allows us to do through a simple measurement, set of measurements of temperatures. We can calculate what is the heat capacity of the calorimeter. And then every time we use that calorimeter, we will be able to add that heat exchange produced by the calorimeter to any other exchanges of heat, particularly in our case of reactions.
Okay, students, please accept my apologies. The original Zoom recording of this portion got a little warped, so I have to redo it. So this is going to look and sound a little different than the rest of your presentation, but bear with me. So now that we know how the calibration works theoretically and why we have to do it, let me tell you what's going to happen in your case. In your handout, you have this page. It's the data sheet for the calibration of the calorimeter. This was done from the lab manual, page 38. And so what you will receive in the online simulation is a filled-in data sheet with all this stuff here. All right. So let me share with you a data sheet from a former student of mine, as I always like to do. This is from my former student, Tony. Tony was a very smart guy. He came from a pretty wealthy family. He went on to build a company out on the East Coast that did a lot of very important engineering projects, some with the military. One thing I heard was that he was trying to build some kind of like an armored suit for soldiers to wear on the battlefield that would protect them. I don't know what happened to that, but I do remember Tony was very sharp, very smart, always talking about the inventions he wanted to make. He could talk a mile a minute. Anyway, this is a sample data set. Notice that you are going to be given 3 trials worth of data. And for each one of those, you have, the room temperature, the temperature of the cold water, the temperature of the tap or warm water, and then the measurements here. Don't forget that, kind of like Tony did here, if you make a mistake, don't blot it out. Just simply cross it out with a single line and then put in the correct number then. Now, what I'm going to do is I'm going to transfer all of this data into an Excel spreadsheet, and we're going to work off of that. Okay, so let's go to our presentation.
Okay, here we go. This is going to be our data set here. And what I do is I'm going to go to a sample here. This is going to be our calibration data, right? So what we do here is I took all that data that you saw there on that spread on that data sheet, and I've copied it over here to an Excel spreadsheet. Notice that we have the room temperature, the cold and the tap water temperatures, and then we have over here you can see all of these. Now, um, let's see what we would do with one data set. So our goal right now is to take, for example, this data set here. I'm going to take essentially this set here. This is for trial number 1. And I'm going to take this data. I'm going to use this to build an Excel graph. So let's see what happens when I tell Excel to give me a graph. Many times what will happen is I will have something that looks like this. And don't forget, you have to format your graph properly with labeling of the axis and a title. So this is the calibration of the calorimeter, trial number 1. Now, here's the problem. You know what? Let me go ahead and erase this here. All right. Here's the problem that we face. Excel decided that I wanted to have very minute, very precise view of this data and spread it out. You can see on the left side there, the y-axis, what you observe is that what Excel did was it took the maximum and minimum data sets that I had, and it spread them out over essentially 0.4 degrees. The problem is my thermometer can only go to 1 decimal. I cannot even achieve this level of precision. And what it does is it gives you a false sense that there's a lot of variation here. So what we want to do is we want to fix this. And please, you can go to our graphing activity the first week, or you can use the help menu in Excel and learn how to take that y-axis and change it to a range that's more reasonable. We're looking at temperatures that are in the low single digits to the 20-something degrees. So I'm going to go in and change this y-axis to a 0 to 25 spread or range. And now what happens is my graph looks so much better, right? Notice again the proper labeling of the X and the Y axis with what property and what units we're using there. Notice the title that we've placed on the graph. And notice that we've also requested Excel to give us the equation of the line. The idea here is that we are not going to be taking the measurement of what happened at the very instant that the two samples of water got mixed. In other words, there's no 0 time data point. What we're going to do is we're going to use this trend line to extrapolate, right? To extrapolate so that we can get to the final temperature here. And in this case, what we're going to do is we are going to use the equation of the line, and we're going to use that value of the intercept there to project this graph over here to what the final temperature would have been after the mixing of water and the exchange with the calorimeter itself. Now remember, our temperatures are only good to about 1 decimal place, so I cannot put in 13.52. I'm going to simplify this to 13.5, and then I'm going to repeat this graph with trial 2 and trial 3, so you'll have 3 graphs, and then you'll put down what are the calculated final temperatures in. Okay? All right, now let me take you back to our document camera, and let's see how we're going to handle the calculations of the calibration of the calorimeter.
Once more, students, I apologize. We had to re-record this portion because the original Zoom recording was very distorted. Here is the data what we just saw. We took 3 trials of calibration data. We showed you how to do the calculation of the final temperature for trial 1 using the graph that we mentioned earlier. And you can see that the final temperature was 13.5. Let me write this in big letters here so you can see it better. T final is 13.5 degrees Celsius as determined from the graph where we used the intercept of the projected trend line to calculate that. Now, how are we going to use this? And again, this is for trial number 1. So let me zoom out a little bit so we can have a little more room here. Okay, very good. There we go. Oh, that's a little straight there. Now remember, according to our theory, because we do this process inside the calorimeter, we said that the total heat transaction for the calorimeter will be the negative of whatever heat exchange happens in the water. Remember, the water is a mixture, well, not a mixture, but a combination of cold and tap or warm water. And we said that the formulas to calculate these things are for the calorimeter would be the heat capacity of the calorimeter times the temperature change for the calorimeter. And for water, it would be minus, and we're going to use the famous MCAT formula. So the mass of the water times the specific heat of the water times the temperature change for the water. This is what we have. So let's rearrange this equation so that we can isolate our unknown, which is the heat capacity of the calorimeter. That's what we're doing this experiment for. So let's rearrange this, and we'll say that C of the calorimeter would be minus the mass of water times the specific heat of water times the temperature change for the water divided by the temperature change for the calorimeter. Now let's review a little bit of what these are. Remember, the temperature change for the water does not refer to the exchange between the cold and the warm water. It refers to the difference between what the actual final temperature of the water was and the temperature that it should have arrived at, which was the midpoint between the cold and the warm water. Okay, so this is what we mean by delta T of the water. Now, for the calorimeter, we have a different transaction because we said the calorimeter started at room temperature and ended up at what we're calling T final. So this would be T final minus the room temperature. And yes, as we will see, what you expect is this is going to be negative because the room temperature was higher than T final. But that negative is going to be compensated by this negative over here so that those negatives cancel out and we get a positive value for the heat capacity of the calorimeter. Let's go ahead and fill in the numbers here. Let's make sure I have enough room here. So we have minus the mass of water. Now we didn't weight the water, we measured the volume. But we're going to say that 100.0 milliliters of water will have a density of 1.000 grams per milliliter. That's kind of a given, and that will allow us to cancel out the milliliters and get grams. The specific heat of water is a constant. We know what it is. It's 4.184, more or less, joules per gram per degree Celsius. Let me get a little bit more space here. And that will allow us to cancel out the grams. And now the final amount here on the top will be the difference between T final, which we said was 13.5, minus the midpoint or average between the two extremes, which were 7.2 and 19. So 7.2 plus 19.0 divided by 2. And again, let me see if I can make a little room here. And that will be in, hold on a second, let me adjust this a little bit. Okay, I'm having a hard time with this thing here. Hold on. There we go. And this is degrees Celsius, which will cancel with this. Okay, what do we have in the bottom? We have the difference between T final, which is 13.5, minus the room temperature, which was 20.0. And again, that will be degrees Celsius. So now we had to put all this stuff in our calculator. Now, let me show you my calculator. Unfortunately, my calculator is not a very fancy one here. So I'm going to have to do this in parts. All right. So I'm going to do the bottom one here. I don't have the ability here to input numbers inside parentheses and do formulas and stuff like that. So let's start out with the bottom. 13.5 minus 20. And as expected, it gives us a negative number, minus 6.5. I'm going to put that in my memory for now. And notice that that value now has two sig figs, because it includes the decimal that we expect to have in all these temperature measurements. I'm going to assume that for the most part, since everything can be read to one decimal, we'll take the two sig figs as our kind of starting point for all these calculations. All right. So let's go ahead and do the top here. So I have 7.2 plus 19 divided by 2 equals 13.1. And I'm going to subtract that from 13.5. And it gives me 0.4. Again, it's only one sig fig, but I'm going to try to keep everything to two sig figs here. And you'll see why later on. Okay, let's continue this operation here. Again, I apologize for the seemingly convoluted way of doing the calculations, but like I said, I have a very simple calculator here. So I'm going to multiply this times 4.184, right? Times 1 gram per milliliter times 100 milliliters, and that gives me 167.36, which I now have to put into the negative. And now I'm going to divide that by what I had in memory, which was this difference here. And as you can see, this is negative. So the negative is also going to cancel out. And I'm going to limit everything to two sig figs here. So this comes up to be 25.74769231. But what I'm going to say here is that this is essentially to two sig figs 26. And you can see the units left were joules and degrees Celsius, which is a proper unit for a calorimeter. Remember, the calorimeter's heat capacity is not a specific heat. In other words, it's not per gram, it's per calorimeter. So what's going to happen now is I'm going to repeat this set of calculations for every one of these trials with, of course, different temperatures perhaps. And then I'm going to put these into my spreadsheet so that I can then use them for further calculations. All right, so let's go back to our presentation.
Okay, this is where we had left off. This was the data for trial 1. After the calculations that I showed you, we ended up finding what was the heat capacity of the calorimeter for each trial. We get those three values, 26, 26, and 16. And the average of those three numbers is 22. Now, here is one of the typical errors that students obtain when they do this. What happens is that they will end up with a value of Ccal, the heat capacity of the calorimeter, that is negative. The main reason for that is that when they combined the cold and the tap water, they didn't stir it properly.
For the third and hopefully last time, I apologize, but we had to discard the original Zoom recording as it was very distorted. So let me try to explain what I meant by the result, the outcome, the error that is produced when you don't mix properly. So what happens is that when you add the cold and the warm water to the calorimeter, if you don't take care of mixing them properly, in other words, to be continual swirling motion, what will end up happening is that there will not be a proper exchange of heat energy. And so what might happen is that now T final, instead of being higher than the midpoint between the cold and warm water, it will actually end up being lower than T1 plus T2 over 2. As a result, when you plug that number in here, this is going to be negative. Then it'll be a double negative, so it'll be positive. The bottom of this operation is always negative. So what will happen is that you'll end up with a calculation of the heat capacity of the calorimeter coming out negative. And this is an error. So what we will do then is, for that particular trial, we will have to discard that value, and we will only calculate the average. So we will use only the positive C-cal to calculate the overall average. So let's say that, for example, for trial 1, you had a positive value. For trial 2, you had a positive value. But for trial 3, you had a negative C-cal. Then what you will do is you would only use trials 1 and 2 results to calculate the average of the heat capacity of your calorimeter. Okay, let's go on.
Okay, I hope that that little example clarified how to do the lab. As we explained, what's going to happen is you're going to receive a data set with 3 trials worth of temperatures and data for a calorimeter, and you will proceed to do your graphs and to calculate the heat capacity of the calorimeter for each trial, and then the average of the 3 trials. After you finish this, please go back to our main assignment page and proceed to the next video, where we're going to explain how we study the heat of reaction, in this case between a metal and hydrochloric acid. Thank you so much. I'll see you later.